So, dear participants, welcome you all again to this day one session 3. It's a second technical session, and this session we have the expert Dr. Anirban Sengupta, Associate Professor from Computer Science and Engineering Department, IIT Indore. It is my honor to introduce Anirban Sengupta. He is a fellow at Institute of Engineering Technology, IET, and British Council Computer Society, BCS. Senior member IEEE, author of 4 books in hardware security, IP protection, CAD VLSI field, author of over 242 publications and awarded with the more than 10 US patents, deputy editor-in-chief, IET Computers and Digital Techniques, chair IEEE CTSOC Technical Committee on Security and Privacy, board member IEEE CTSOC Technical Committee member. I welcome you all and I welcome Anirban Sengupta sir for his invited expert talk on this security perspective for IoT applications. So over to you, sir.
Okay, thank you, Dr. Nima. It's been a privilege to be part of this FDP, and thank you again for having me here. Okay, so without much ado, I would like to start today's talk. So I've been asked to give a talk on hardware perspective of the security from the underlying core of IoT. So I wish to talk on biometrics authentication for hardware security and trust, which is a very important part of IoT hardware. If you think from the perspective of securing the underlying hardware used in IoT frameworks. These are some of the books that I will be referring while I give my talk today, and interested readers may also read the book for more details. So, as you know, in IoT, it's a framework and combination of different types of things, which we call as the Internet of Things. That could be IoT sensors, microprocessors, dedicated hardwares, and so on. And all of these hardware cores eventually needs to be secured against external attacks. So my perspective is, if we think of securing these hardwares, we need to understand what hardware security and what intellectual property cores are. And as we know, it's an emerging area of research for the semiconductor community, where computer science researchers have a very important role to play in developing algorithms that can secure the hardware. The main focus is on protecting the designs against standard attacks such as reverse engineering, counterfeiting, forgery, malicious hardware modification, and so on. These type of security modules can be broadly classified into 2 types. The first is called authentication-based approaches, and second is called obfuscation-based approaches. In the second type, which is the obfuscation-based approach, it can again be broadly subclassified into 2 types, which is structural obfuscation, where the goal of the designer is to convert the respective hardware structure in a form which is significantly more difficult to reverse engineer, but offers the same functionality as the original. While in case of the active type of obfuscation technique, which we call as functional obfuscation, the main goal is to lock or encrypt the design using predefined valid sequence of secret keys. What type of hardware accelerators or hardware platforms are often used in IoT frameworks? Okay. Some of the ones which I've put down here are very popular and often used, specifically in the domain of DSP and image processing. They are called finite impulse response filters, JPEG codecs, convolution filter, BFT, DCT, and brightness and contrast filters. Some of the techniques or algorithms that we have devised for securing hardware accelerators used in IoT platforms for these DSP and image processing applications could be cryptosteganography based, integrated watermarking and structured obfuscation based, biometric fingerprint based, facial biometric based, as well as techniques using cryptosteganography and hash chaining. We have also devised several cat tool products which are widely used in the scientific community, and they have been accessed more than 2,000 times so far in the last few months. And it has been publicly released from our group in September 2020. And they are currently hosted in University of Florida Cybersecurity Research Center. So these are these 4 tools which are available online, and one can use it for the research projects as well. Okay, now let me talk a bit on the other branch of hardware security, which is also called as IP core protection, and it is often more popularly known as forensic detective control techniques. So what these techniques do is that instead of providing prevention of the attack, they actually provide detection. Okay, if there is any sort of malicious activity that has happened, it can detect the malicious activity. For example, if there is a counterfeit, okay, in a particular IoT product, it can detect the counterfeit component. If there is any sort of piracy that must have happened, it can detect the pirated components. So these are algorithms that focus on detecting piracy, detecting counterfeiting, detecting cloning, and so on. So what are these methods? So these methods are mostly watermarking based. Watermarking is nothing but a secret mark that are implanted or embedded into the hardware of the IoT platform, so that we know which one is authentic and which one is a counterfeit. Okay. The result of using a counterfeit component in an IoT hardware is very dangerous, as it could lead to several fatal consequences, including explosion of the respective hardware, or it could lead to malicious consequences in the form of hardware trojans. So these watermarking techniques could be single-phase hardware watermarking, could be multi-phase watermarking, could be multi-level watermarking, hardware steganography, and digital signature-based watermarking. On the other hand, when we are talking of hardware security from the obfuscation perspective, that is when we want to thwart or hinder the reverse engineering process, because using the reverse engineering process, an attacker tries to get hold of the design's functionality, its internal structure, and tries to secretly embed a Trojan logic or Trojan horse in a secret location such that it becomes non-detectable during normal validation phase. So some of these obfuscation techniques that can actually hinder or thwart reverse engineering process could be compiler transformation based obfuscation, could be high-level transformation-based obfuscation, hologram-based structured obfuscation, as well as functional obfuscation, which is nothing but the encryption of the entire, logic design or logic gate. These could be further secured if we augment the obfuscation with other security blocks or crypto blocks such as AES and SHA and other lightweight ciphers. From the perspective of designing a dedicated processor or dedicated IP that are often used in IoT frameworks, as I said, there are certain popular applications like the ones in image and DSP, and they're often designed using techniques known as high-level synthesis. So these HLS frameworks, okay, there are some commercial HLS tools, there are some academic HLS tools. So these HLS tools play a very vital role in integrating the security algorithm, okay, when we want to design a secured hardware for such platforms. So the primary input will be in the form of a module library and the DFG or C code of the respective DSP application, its corresponding spec and constraints, and the security algorithm will play the role of incorporating or embedding the security constraints into the design while the synthesis process is going on, in order to finally generate a data path and controller of the processor at the RTL level. Okay, now let me talk a little bit on what biometric fingerprinting does. So it's a forensic detective control mechanism often used for securing hardware accelerators, and the respective CAT tool product of this has also been publicly released in the scientific community a few months back, and it is also currently hosted at University of Florida Cybersecurity Center. So what this basically does is it uses an IP vendor's fingerprint to convert it into its respective digital template. And once a digital template is made, then it will be further converted into its respective constraints to produce an anti-pirated secured hardware accelerator. that is able to defend against piracy as well as fraudulent claim of IP ownership. So fraudulent claim of IP ownership is also a very important problem because a lot of fake ownership claims are made by different IC or IP vendors for the IoT hardware. So let's look into the algorithm once. So we start with the input fingerprint captured through any optical scanner, and then we go ahead with performing some pre-processing steps such as FFT enhancement, binarization, and then thinning. And then we perform the minutia extraction and convert this minutia points into digital template, which is nothing but a sequence of ones and zeros. And then we map them into the respective hardware security constraints using some encoding rules or mapping rules that is devised by the designer. The next phase is to implant these security constraints into the hardware during the register allocation phase of HLS synthesis process. And finally, we receive a biometric fingerprint implanted hardware accelerator design. So in the binarization, we can see how the fingerprint looks like, and then we convert that into a thinned image where we reduce the pixel width, and then we have the minutia point at the end where the two types of minutia points could be bifurcation or could be ridge endings. So we have the captured fingerprint image, then we have the binary fingerprint image post enhancement, then we have the fingerprint image post applying thinning, and finally we have the fingerprint image with minutia points located. So the question is, what type of fingerprint must be used and how does fingerprint impact the final hardware security constraints? So for that, we did a study to find out what is the impact of the final security constraints or the complexity of the security constraints based on what type of fingerprints have been used. So we have taken a few different types of fingerprint images, and we've seen that the minutia points greatly vary, as well as the digital template size also greatly varies. So for example, in case of the first and third one, the total size is beyond 500 bits, whereas in case of the second one, the size is around 350 bits. So subsequently, the number of zeros in the digital template and the number of ones also affect and change accordingly. These numbers are useful because we have the encoding rule based on the numbers of zeros and ones accordingly. Similar analysis can also be made if you talk about different fingers for one individual. Again, for the same person, different fingers have different minutia points and different digital templates, as well as resulting into different number of zeros and ones. So that affect the security strength, which we call as the probability of coincidence in technical terms, the security strength of the final hardware accelerator. So once we implant such a fingerprint or facial biometric data into the hardware, we could see that the hardware, once designed, would appear to look like this. This is an example made for JPEG compression, decompression IP. And the red mark portion on the top actually indicates that this is where the facial biometric or the fingerprint biometric secret data is implanted. But optically, by visual inspection, an attacker wouldn't be able to figure this out. How do you detect such a biometric fingerprint in a hardware accelerator? So the first step is we have to feed the digital template of the embedded biometric fingerprint on one side, and we'll have to feed the digital template of the genuine IP vendor's biometric fingerprint under test. We'll have to match the number of zeros and ones in the digital template. If there is a matching that happens, then we move to the next condition box where we check the matching of the positions of the zeros and ones. If both the numbers as well as the positions they match exactly, then we know that this is the original digital template of the authentic IP and the ownership is awarded to the true IP owner. If in case there is a mismatch in the number of zeros and ones right away in the first step, then we know it's a counterfeited design. So in that case, we don't proceed further in matching the number of positions of zeros and ones in the digital template. So the number of minutia points for different fingerprint images also vary, and we've discussed it as well just some time back that in different fingers, this variation in minutia points is very likely. And accordingly, since the number of minutia points vary, accordingly the number of digital template size will vary and the number of security constraints will vary. So certainly the probability of coincidence, which is a security metric used for watermarking, steganography, and digital signatures, that will also change drastically. So more number of constraints, the probability of coincidence will be lower and lower. Higher is the constraint, so we'll have a lesser probability of coincidence. If the number of constraints embedded is actually low, then the probability of coincidence will be high, which is undesirable. It's also important to note that when we want to secure a hardware, whether we use it for IoT framework or any other platforms, whether we directly put it in a consumer electronics products or we put it in a portable gadget, eventually we also have to balance the design cost versus security. It cannot be only security that's an objective. It has to be design cost versus security, because we not only would like to optimize security, but we would also like to optimize the design cost. So therefore, it mandates to have a comparison between the baseline design and the biometric fingerprint implanted design to see what type of cost overhead we achieve. So based on the analysis we have seen here that there is 0% cost overhead that is achieved in case of biometric fingerprint implanted design. The reason is the baseline design provides us sufficient flexibility in making local alterations in the register allocation phase. And as a result of that, we don't need to accommodate extra registers that will affect the design cost of the hardware. So this is another type of approach which is called as hardware steganography, and this slide actually reflects how does the encoding and decoding process works. So how is a steganography different than a watermarking is as follows. In case of watermarking, what typically happens is the signature size and its encoding rules are already predefined by the IC or IP designer or by the hardware designer. In case of steganography, what happens is the signature constraints are actually generated through an algorithm. Okay? So the signature is not predefined in this case. That's the only difference we have, and sometimes in the scientific community there is a belief that steganography can be more secure than watermarking in many aspects because of this reason. So in the encoder stage, we have the processing of the designer specific hardware steganography constraints, and then we have the embedding of that into the RTL design phase of the HLS framework. And at the decoder stage, we'll try to extract the stego constraints from the IC/IP code, and then we perform the verification to detect the steganography mark or stego mark. So this decoding phase basically helps us in finding the proof of the original or fake IC/IP maker. It also enables us to detect the IC/IP counterfeiting, and finally it also helps us to detect the IC/IP cloning process. This is yet another example of another image processing application known as discrete cosine transformation. So this is the hardware for 8-point DCT, or we can call this as a application specific processor for 8-point DCT that we have designed at the RTL level using HLS framework. And this is before any steganography was implanted, and this is after this steganography was implanted as a secret mark. So optically there is hardly any difference that is visible to an attacker to identify where the stego mark is located. But for an attacker, there is it's a clear-cut distinction because the attacker knows where the secret marks are embedded into the design during synthesis process. Now let us move into the third category of algorithms or approaches, which is known as digital signature-based technique. They are also used for protecting an IP or securing the hardware. These are basically crypto digital signature approaches, which incorporates two important security modules. First is crypto hash function SHA-512, and second is crypto encryption function RSA. And it also uses multi-level encoding process. The generic steps of generating digital signature could be to first generate a bitstream representation of DSP code, performing SHA-512, post-processing step number 1, which is to perform SHA, and then we have followed that with RS encryption, and then post-processing step number 2. Diagrammatically speaking, the first step would be to capture and have an IC watermark information from the design itself. So instead of taking a signature from the vendor, here the signature is actually created using some encoding rule from the design itself, which is a DSP application. Then we subject that to crypto hash function, which is SHA-512, and we produce a digest or hash of the value, which is then subdivided into different blocks, and then it is secretly signed using the ICIP vendor secret key. So using RSA algorithm, then we finally generate the encrypted values of each of these chunks of blocks, which are further concatenated to produce a large sequence of encrypted signature, which acts as the digital signature of the IC or IP vendor. The details of the technique is as follows. We first have the DFG of the DSP application, which is the data flow graph of the DSP application. We also provide certain resource configurations, which is just acting as a constraint to your design. How many adders, how many multipliers, how many dividers, how many exponent blocks, and so on. In the pre-processing block number 1, we construct the SDFG, which is the scheduled data flow graph, and assign the storage variables. And then we generate a bit stream. We calculate the digest of the bit stream value, and then we divide the bit stream digest into m blocks of size n bits and convert each of these n bit blocks into decimal value. Once we have the decimal value, then we employ RSA encryption on that using RSA private key. And finally, we construct a bit stream from the encrypted decimal value post concatenation. Once the concatenated value is arrived, then we encode the bit value of the encrypted bit stream to finally produce an embedded digital signature in the register allocation phase that is useful for embedding the secret security constraints into the design of the DSP. And finally, we have the digital signature embedded DSP processor. So this is just an example. So the role of RSA encryption is basically to sign the hash digest of the vendor secret mark information to ensure authentication of the genuine owner. So we can have a 120-bit input as shown here on the first column, and the encrypted decimal output as shown in the second column. And the corresponding binary value will be as follows. So each of these could be concatenated further depending on the number of blocks that is signed by the RSA module. So once we have this, then we need to embed the digital signature into the design. So for that, what we need is basically the encoding rule of the zeros and ones, because we have converted that to binary. So there has to be a encoding for bit 0 and encoding for bit number 1. So one of the possible encodings would be to add an additional edge in the colored interval graph of the register allocation phase between the node pair prime, and bit number 1 would be to have an additional edge between the node pairs even in the colored interval graph of the register allocation phase. So based on that, we can add these extra artificial constraints into the design as secret mark of the DSP. So we did some analysis of the design cost as well to see what is the design overhead after implanting the crypto digital signature. The design cost is basically a hybrid function of normalized latency of the design and normalized chip area. And what we see basically is that we have the latency LT of the scheduled design, which will be normalized by dividing it with LMAX. And 5152 is basically the user weighted functions, which is fixed usually to 0.5 to give equal preference or weightage to both normalized latency and normalized area. What we see here is that depending on the size of the signature, usually beyond 15, the size of the signature grows from 30, 60, 120 to 40, but there is not much effect on the hardware cost overhead in terms of the normalized latency and area. If we evaluate the probability of coincidence, which is the evaluation of the robustness of the design, using the function 1 minus 1 by c whole to the power s, where s denotes the digital signature size and c denotes the number of colors in the CIG, we see as the number of size of the digital signature grows, the probability of coincidence reduces, which is a good sign or good indication because it indicates that the design is robust. Let's skip the slide. We have spoken a bit on that. In case of the biometric fingerprint, one important thing that we should remember is that when we extract the minutia points after the thinning process, we usually employ a crossing number algorithm. Okay, and if the crossing number value is 3, we know that it's a ridge bifurcation, and if the crossing number value is a 1, we know it's a ridge ending. So that's how we produce the minutiae point after the thinning process is performed in the reprocessing phase. Now, based on the minutiae points that are available, we have devised a technique in order to extract the binary value from there. So we have the position of x and y, okay, in the x and y axis. We have the value of m, which indicates whether it's a ridge bifurcation or ending, and then we have an angle d, which actually says that what is the value of the angle when we measure it clockwise from the horizontal axis. So basically, it's 34 degrees for the point that you see here on the dwarf of half of the screen. Is clockwise from the horizontal axis. So once we have these values 190, 45 for example, and then 3 and 34, we'll try to concatenate all the 4 values into its respective binary value to produce a signature of that. Similarly, this will be done for all the rest of the minutiae points, and when we have the collective value, we'll try to concatenate the entire thing to produce a digital template of all the 15 minutiae points, which is shown here, which is usually a sturdy value of around 350 bits or more, comprising of more than 148 zeros and 202 ones. Once these are done, then based on the mapping rule of the ESL synthesis, we can again embed that into the DSP design, for example, in JPEG codec as an application, and we can find out what is the resources pre-embedding security constraints and what are the resources post-embedding security constraints. And we can also find out the number of multiplexers and demultiplexers, as well as the number of FUs in terms of multipliers, adders, subtractors, dividers, and so on. So I'll skip these. We have already spoken a bit on these. In case of the security analysis, if we try to embed the biometric fingerprint into 2 layers, one is in the raised allocation phase and second is the functional vendor allocation phase, then the probability of coincidence function will change slightly and the value of PC will even be more stronger. So once you've compared that to a watermarking approach or with a cryptosteganography based approach, we see that the biometric fingerprint actually produces much lesser PC value, which indicates the robustness and security of this approach. Now let me move a bit on the facial biometric approach for hardware security. So this is also one of the novel approaches that we have devised in our lab that leverages unique facial biometric information to secure hardware accelerators. It's a contactless mechanism for securing hardware accelerators, and it has low implementation complexity and higher robustness during authentication and verification process. It also offers zero dependence on external factors and is completely non-vulnerable and non-replicable technique. In facial biometry, what happens is we devise an algorithm to generate the facial signature, which acts as a secret information for embedding the secret information in the HLS framework. The HLS framework works under the influence of module library and the resource constraints, as well as the algorithmic description of the DSP application. So this slide shows the flowchart of the entire approach. So we first start by capturing the facial biometry with grid size and spacing. We generate the nodal points on the facial image, which will of course depend on the facial feature set, that what type of features are used and what type of features we believe are going to be a stronger security parameter compared to the others. We then designate the name convention on the nodal points and we generated the image with facial features. Then we determine the facial feature dimensions between the nodal points for selected features. We decide the feature order and then we finally produce the facial signature. We convert that to hardware security constraints using the encoding rule, and then we embed that into the design using HLS to finally produce an RTL design of the implanted DSP with the facial signature. This is just an example. We have, for example, an image with the nodal points P1 to P18, and these nodal points are the ones that are chosen by the designer in order to structure or formatize the feature set that he has chosen. So for example, the 11 features that were chosen as part of devising this technique was the height of the forehead, which is the dimension between P1 and P2, the height of the face, which is between P1 and P18, the width of the nasal ridge, which is between P2 and P11, interpupillary distance, which is between P3 and P4, ocular breadth, which is between P5 and P6, biocular breadth, which is between P5 and P8, and then we have intraocular breadth, width of the face, width of the nasal base, nasal breadth, and oral commissure width. So all of these 11 features are part of the facial biometric, along with the nodal points between P1 to P18 that were used to produce the final facial signature. The corresponding coordinates that are available is used to calculate the Manhattan distance between the two. So for example, if you want to calculate the distance between P1 and P2, we'll have to employ x1, y1 minus x2, y2. Once we have this done, then we get the framework of the facial biometric and we convert that into its binary representation. By concatenating all the binary representations, we see that we finally have produced a digital template of the skeleton of the facial biometric. We notice that the varying lengths of the feature dimensions in the binary representations, this lack of uniformity is actually a very good thing because it produces an advantage as the adversary has no clue about the points of concatenation, making the extraction of the individual dimensions literally impossible. So once we have the application ready, we'll try to convert that scheduled graph into a colored interval graph, and we'll try to embed all the different facial features. But before we can do that, what's important is to also decide what is going to be.
Sorry to interrupt you. Some noise is coming out from. I don't know where it's.
Yeah, Vaibhav, tell me please.
Sir, some noise is coming out from that.
Probably there is some background noise in the construction happening.
Okay.
Yeah.
Okay.
So sorry about it. I don't know, there's some construction going on in some.
No, sir. Thank you, sir. You can continue.
So what I was saying is basically the feature orders also play a very important role because in the feature order, it's important that in which order or which combination the number of binary bits will be embedded into the design. So for example, if we have 11 facial features, these could be in the order that is shown here on the right on the top, and the number of features will produce an 81-bit information. If we reduce the number of facial features, for example, we can reduce it to 6 features, and the number of security information in terms of the number of bits will reduce to 43 bits compared to 81 bits earlier. It is also possible that we can have the same size of the signature of the facial biometric, but the order of the facial features can be different. For example, in the first case, the facial feature orders are vastly different than the one in the second case, although they have the same sizes. So this is an example of the DCT, discrete cosine transformation hardware, where the colored interval graph after implanting the facial biometric looks like the one shown on the right side. These extra red colored edges are the ones which are implying the newly embedded edge as security constraint, while this is before the facial biometric was implanted. So once we have this newly made colored interval graph, we can again re-accommodate the information here in the newly devised scheduled data flow graph to reflect the information what we have here as well. And once we have the new scheduled data flow graph, we can convert that into an RTL data path of the corresponding application as shown here. So these red boxes show the changes in the variables allotted to the registers as a result of the embedded facial biometric. And it's very hard to detect from an attacker's perspective where the facial biometric is. From the security perspective, it is also important to know that an adversary also, besides having to get access to the facial biometric information, also needs to know the following information in order to crack or reclaim the design or pirate the design. For example, he needs to know the precise coordinates of the nodal points, needs to know the type of features selected, needs to know the ordering of the features, needs to know the number of zeros and ones implanted, the positions of the zeros and ones, and finally also needs to know the grid size and spacing of the facial biometric data. Let us also have a look at the impact of the varying facial signature on the generated hardware security constraints. As you see here, for different images, we see that the facial signature also changes quite a bit, and the varying lengths of the digital templates is a reflection of the fact that the size of the facial biometric signature will also change in terms of zeros and ones. So more the number of features included, more likely the template is bound to differ, at least in one bit position, thereby enhancing the security perspective. In terms of the security analysis, we saw that once it is compared with the watermarking and steganography based techniques, the facial biometric is in fact much stronger in terms of the probability of coincidence and robustness, because if you see the comparison between the different images or the proposed biometric fingerprint or biometric facial approach compared to hardware steganography, we see that the PC value is in fact much lower compared to stego or watermark. So which in fact is what we all probably understand, that facial biometric and fingerprint is much more secure than going for watermark and steganography. In terms of the design cost, we see pretty much similar as what we expected, that the design cost overhead is nominal or almost 0% in most cases. And when we have plotted a trade-off between probability of coincidence and design cost, we see that the basically the design cost remains pretty much same, and the PC value reduces gradually as we keep increasing the number of features from 8 to 11. So these are some of the tools that I was referring to, and these tools can actually be used by any researchers working in the field of hardware security or IoT hardware security. Yes. Anybody has any question? If somebody wanted to say something. Okay. So basically we have this faciometric hardware security tool, and then we have this crypto steganography hardware security tool, and this key triggered hash chaining driven steganography tool. All of these tools are actually capable of providing hardware security and IP core protection for the IoT hardware in terms of securing against counterfeiting, cloning, forgery, and reverse engineering. So these are the 4 threat models that we are targeting. When I'm referring to reverse engineering, I'm also trying to indirectly say that if an attacker is unable to reverse engineer, then he or she would also be unable to insert Trojan in the safe locations that would evade detection. Okay, so indirectly it also safeguards against functional Trojans that are quite prevalent in these third-party intellectual property codes. So I would like to conclude today's talk by saying that the future of VLSI or IoT hardware is on energy security trade-off, devising algorithms and techniques for performing trade-off between energy and security, and that's the way going forward. Thank you, and I'm open for discussion and questions.
So any participants have any doubt or any questions? The session is open for the participants. So I have one question, Ariman sir.
Yeah, please.
So in case of encryption, why do we only always prefer a XOR gate and AND gate?
Yeah, so basically XORing is a very popular technique for performing encryption, because in XORing what you can do, you can use the values of zeros and ones to either negate or produce the same value. And mostly XOR gates are also very popular when we try to build complicated hardwares, which are always available there. And once you perform the synthesis and implementation in the tools, we will always see that these XOR gates are always broken down into further primitive gates like AND and OR. In any case, we can always implement using AND and OR. So XOR gates is an automatic choice in such cases.
Okay, sir. But I have one question in the chat box.
Okay, let me have a look. Please.
Madhu Kumar.
Okay. What were the lightweight cryptography techniques that we used for IoT? So lightweight cryptography techniques. So basically, see, RSA is anyways a lightweight technique. Okay, RS is anyways a lightweight cryptography technique. You can use SHA. SHA is also like secured hashing algorithm is also a lightweight technique. AES is not, because advanced encryption standard is usually very heavyweight. If you want to implement it in hardware, that's actually very hardware heavy. It incorporates and uses a lot of gates. I will not recommend AES, but RSA and SHA-512, these are pretty, or SHA-256 are pretty much lightweight ciphers that can be used. Or you can also go for other sort of ciphers like the ones which, like for example, uses simple encryption techniques. So they are all possible. But again, you will have to do a trade-off between security and the hardware cost, right? If you go for very lightweight cipher, it may not provide you as much security, but it will give you a lot of advantage in terms of overhead. But if you go for a strong cipher, it will give you a very strong security, but also the overhead will be large. So there has to be a trade-off there also.
It depends on the application, what application you are using, and according to that, you have to select that.
Yes, it also depends on the application, depends on how much you can afford to spend on your hardware in terms of power, chip area, and so on. So there are so many things.
So can we introduce this encryption technique in Raspberry Pi and all this?
Yes, you can do that. As long as you're using a custom hardware, it's possible. You cannot use it for hardware that you directly purchase from the market. But if you're devising or designing a custom hardware and using it somewhere in your IoT platform, then this can be done.
Any other question? Any further question from the participants? So you can ask the question or you can type a question on here.
Yeah, please feel free to go ahead and ask me questions.
So in case of very low power, means people are talking about the zero powers IoT systems.
Right.
So in that case, this encryptions, what kind of encryption techniques they generally use or preferably use for that?
Yeah, see, I think zero power techniques or zero power IoT applications are actually very hard in real life, specifically considering the growing demand of the complexity of the applications. It's actually very hard, but I would again recommend, if you're talking of lightweight ciphers, RSA is the best choice, followed by SHA-512. If you go beyond it, it'll be very hard, honestly. I would never recommend to go for AES, but I'll always recommend you to stick to RSA and SHA, not beyond it. If you're only looking for low power applications, which is the case in case of IoT. But at the end of the day, when you want to implement it in hardware, it also has to be power optimized. So there has to be optimization algorithms employed to find out what is the optimal architecture when you devise or design the hardware for these RSA or SHA-512 encryption techniques.
So when we design a low power system, so various abstraction levels are there.
Right.
We can have algorithms at the abstraction with architecture level, or we can have at the transistor level also.
Right.
So means according to you, what level is the best means where we can target a low power design?
I think low power designs, if you're only talking of ciphers, then RTL or gate level is the best choice. There's no point of raising it above it. But if you're talking of devising applications for IoT hardware, which are, for example, custom processors from different domains of multimedia or image or video processing or codecs, then I think it always has to start at the architecture or algorithmic level, and therefore bring it down into RTL and corresponding into gate level and so on.
And the tool which you have suggested that you have developed that tools, so we can use that tools. I mean, they are open source tools.
Yes, they are open source tools. They can be downloaded. They can be used in research projects. They've already been used more than 2,000 times by different researchers across the planet. So they're already currently hosted in the servers of University of Florida. So the link that I pasted right at the end, they can be used for downloading.
Okay, we just download and we can use that for.
Yes. It's free of cost.
Okay. So if no more questions, we can close this session.
Okay, I think applicants or candidates can get in touch with me offline also over email if you have any other questions. Yes. And the slides will be made available to you by Dr. Nima, so you can get in touch with him as well.
Thank you, sir. Thank you so much, Anirban.
Okay, thank you so much and wish you all the best.
Thank you. Thank you so much. So participants, this is the last session, today's last sessions, and we'll provide you this link for that attendance. If the link will not provide, then we'll consider the second session attendance for all participants. So thank you all for joining session one, day one, 3 sessions. Tomorrow we'll start tomorrow morning, 10 o'clock, we'll start with the Sudev Das Gupta sir. We have a talk from the Sudev Das Gupta sir, then followed by that, the Dr. S.K. Vishwakarma from IIT Indore, and then the last talk is from the Salesh Singh Chauhan from Luleå University, Sweden. So they are very experienced and they are very expert in the case of IoT system design. So I hope you will enjoy this session, technical sessions on IoT. If you have any query related to the FDP or any kind of query related to that course, you can feel free to ask me any query, any question about that workshop.